Okay, let's get started. All right, so last lecture finished off talking about the texture cache. Okay, so I hopefully gave you some brief introduction on how textures work. Did anyone know that before? How texturing worked? Not really? Okay, hopefully it was at least mildly instructive so you sort of learn how graphics or anything works a little bit. Texturing is super important because otherwise your scenes don't really have any color, right? And capturing that locality is important to make good use of bandwidth. So they built the texture cache, and sometimes, depending on the GPU design, they bolt the global memory accesses in CUDA or in OpenCL, if you're using an AMD machine, onto the texture cache instead of onto the shared L1D shared memory structure. Okay, which is why part of the reason why we go through this. Okay, because what does a texture cache even look like? So we finished off last lecture taking a look at this sort of high-level block diagram of the texture cache. And remember, the primary purpose of this thing is not to reduce latency to memory, because we don't really care so much about the latency of each individual fragment. Fragment is basically the section of the screen that you're trying to render. What we care about is finishing all the fragments in an efficient, that's what matters. How long does it take us to do the whole scene? So the texture cache is built to be a space-efficient way to initiate a whole bunch of misses so you can saturate memory bandwidth while still capturing that spatial locality across the texture accesses that you'll have, right? Because you're going to access, that little smiley face we looked at. You're going to render one piece of it, then you're going to render the next piece of it. So there's a lot of spatial locality. We want to capture it, and we want to do it in an efficient way. Okay, so the basic idea here, and it's kind of, it's sort of a clever idea, is that we're going to have the tag array run ahead of the data array. So the accesses are going to come in the load store unit, and they're going to insert themselves in the tag array, even if the data isn't there yet. Because we're going to make the assumption that by the time the access gets to access the data array, which is separated by this, relatively long FIFO, so a queue that every cycle is just going to move the particular fragment you want one step closer. By the time it gets down here, even if it was a miss, it should be in the data array, or very close to being in the data array. Okay. And if it was a hit, it'll be there, and you'll just go ahead and access it. The footprint of these things is relatively small. So texture caches, they got a little bit bigger, but 16 to 48K kind of space-wise. And if you look at that in contrast to the L1 data cache or shared memory on modern GPUs, which is like 128K, it's a lot smaller. And generally that's because the textures don't tend to be super large. You tend to have many little textures that you're rendering when you're rendering a scene. And we don't want a big associative MSHR. So the real sort of reason here why we built this thing at all is because in a normal cache, you have two associative lookups on a miss. You have an associative lookup to check if it's a hit. And then you have another associative lookup in the MSHR to see if there's a pending miss for that miss if you miss. In this structure, I'm only going to do an associative lookup once, and it's going to correspond to both hits and misses. I'm just going to use this tag array to do the associative lookup only once, and and then basically ensure that by the time this thing gets to the end of this FIFO, it's going to be in the data array or very close to in the data array. So that's sort of the win. You get rid of two associative structures, and you can just have one in the tag array. Questions on this? All right. So how does this work? So the load store unit will send the access. So a texture access will, say I want these. It could be 1 pixel or texel, or it could be 4 texels. Usually you want 4 because you're grabbing the 4 that's sort of closest to that interpolation point, right? Remember we looked at that diagram of the MIP maps. Your distance is somewhere in between. So you're going to grab 4 texels from the top MIP map and grab 4 texels from the bottom MIP map and blend them somehow to figure out the color at the particular distance that you want. So you're going to grab it, probably 4 values in each of these operations. Then you check the tag array. You check to see if it's in there or not. If it's in there, if it's a hit, that doesn't mean it's actually in the data array yet, but that means that another access has come in and inserted itself in the tag array. It could be in the FIFO still. That by the time I get to the front of the FIFO, I know is for sure going to be in the data array. Okay. So that hit says that I've already loaded this particular block before, but that load may just be right in front of me, right? It might not actually have come back from the main memory system. It may just be sitting immediately in front of me. But in effect, I've merged the two, right? So you'll notice that this is sort of like MSHR merging if you've got many misses in play. It could be the case that it's already in there. And you do have to keep both of these in sync, right? The replacement policy for both has to be synced up, and the sizing has to be synced up, but it's effectively running ahead of what the data array should look like. So on a hit, you get placed in this FIFO. It takes you some time. So we sit around because the data may not actually be in the data array yet. So it'll wait its turn as it sort of cycles through each of the stages of this FIFO until it reaches the head. When it reaches the head, there's basically some meta information in here to say, which data entry I want to access based on the tag hit that I had in the previous lookup in phase 2 up here, right? There's some meta information that says you're at index X. So I'm going to go to index X when I get down to the head of the FIFO. So then you get there, you look up the data, and then there's a built-in filter. So there's basically some kind of combinational logic in here because I know that I need to do this filtering between, this is a very common access to MIPMAP layers, and I need to blend them together. So I'm not going to I don't want to put that in a register file and do a bunch more instructions to try to do the filtering if I know I'm just going to keep doing this over and over again. So there's some basically instruction-specific hardware to do the filtering, right? This is built assuming you've got MIPMAPs. This is built assuming that you want to load 4 and 4 and then blend them together in some way. And the instruction itself, like the texture instruction that the core issues, has all that information in it. Like these instructions are kind of crazy looking. They have many input operands. They're complex instructions because it's loading from texture places and it's trying to do this filtering as well. So it reads the data out and then it sends it into this texture filter, which can basically try to blend together whatever output that you're trying to write to. Okay, and that goes into the register file, right? The end result of a texture load blend operation is some color value that's stored in your register file that you'll probably then write out to memory with a different instruction. Okay. Questions on this? So again, graphics. It's sort of the same as compute, right? You still have a register file, you still have a main memory, you're just doing like different types of blending operations versus, what traditional compute looks like. All right, so what happens on a miss? So on a miss, you get to the tag array and it's not in there. That means that it's either been evicted, so you've seen this before, but it's gonna be evicted by the time you get to the head, right? Or you just haven't seen it before. So then you go to another queue. So you have a FIFO here that's going to, queue up the requests that are missing. We need a FIFO because memory might not be able to keep up. There's buffers everywhere in modern systems, right? So you've got a simple FIFO here that's going to go to the memory system once the memory system has enough capacity to take the request. And when you miss in the tag array, we're still going to insert an element in this fragment FIFO. And it's still going to get, cycled each time until you get to the head. And the hope is that the stuff is back from memory by the time you get there. If it's not back from memory, you have to stall the FIFO. The whole thing has to wait, right? Because it's possible that there's some disaster in memory that makes it take longer than the size of your FIFO that you had. But we size this such that in the common case, it's usually back or very close to back. Okay, so you send the request down to the lower level of the memory system, and you place the fragment in the FIFO. Now, we do need a reorder buffer here, because GPU memory systems reorder things like crazy. If you're taking 666, like memory reordering, aggressive things that affect consistency, GPUs, especially for graphics, they just reorder stuff like crazy, because there's not really many inter-thread dependencies, especially in graphics. So you're sort of free to take all your memory accesses and be as aggressive as you like with them in the system to try to optimize throughput. So the memory system is going to reorder your accesses. A very simple case of this is if, the first access in the miss FIFO hits in the L2 cache and the second access in the miss FIFO, the first one misses and the second one hits, right? The second one's going to come back earlier. And because I've got this fragment FIFO, which is dependent on the order, right? I can't rearrange things in this FIFO, that would be expensive. It's dependent on the order it went to the tag array. You have to make sure that when it comes back, it's in the same order that you sent it in. So there's a reorder buffer here to try and fix the ordering, so that way, you get the exact same order. Make sense? Yeah.
Oh yeah, 100%. So for the hit, for the hit case, so
Yeah.
if so do you have that some logic to make sure that it is evicted like while it's in the FIFO, like
So it won't be evicted because what do you mean? So like in here, right?
yes.
So if these are the same, if you sized everything appropriately, then you're effectively keeping the state, after some N accesses have come back, right? So you could sort of think of it that way. So it won't get evicted in the time it's in the FIFO. Okay, because if you're doing LRU replacement on the tag array, so you have some stream of accesses you're doing LRU replacement on, you're going to do the same LRU replacement on the data array, and you're going to process the tag array and the data array in the exact same order. Then by definition, a hit up here will correspond to a hit down here and vice versa. If you guarantee the order, which we are doing because we're doing this reorder buffer business. Okay. Make sense? So even though it's not actually happening temporally at the same time, it's logically happening at the same time because the orders are enforced and the sizing is the same. Does that make sense?
Okay, yeah.
Good question. Yep.
Are the request FIFO and fragment FIFO the same size?
They don't have to be. I mean, in theory, you probably need a smaller miss request FIFO because you'll have some hits. So you need more entries to handle the hits in the fragment FIFO than you need in the miss FIFO. In the worst case where everything misses, then this was kind of pointless anyway, right? So why did we build it? So, these are the fragment FIFO. It's not to scale, like I know the box is bigger, but it sort of is, right? In some ways that it is bigger. It should be larger. Good question. Other questions? Okay. The miss request FIFO will be dependent on how much memory bandwidth you've got coming out of the cache. Yeah. Okay. Yeah.
Is this memory separate from so is the main memory also separate for texture versus the data?
No, it'll go to the L2 and it'll be HBM. Okay, when you load textures into a GPU, you're in the, GDDR or the HBM, depending on what the, what GPU you're using. So it'll be shared with the rest of the global memory space. So you buy a card that's got 4 gigabytes of data and you're using 150 megabytes for textures, that's taken out of that 4 gigabytes. Okay, other questions? Even though this seems weird because it's graphics, I mean, it is just loads and stores and math, right? Everything that we operate on is just loads and stores and math. And there's no special, after you get out of the texture cache, it's treated sort of like there are some other operations when we start to look at the L2 where we can do operations sort of like a PIM out in the memory space that graphics does. We'll talk about when we get there. But generally, you're just doing loads and stores to the memory system. Okay, other questions? Okay. All right, so then the thing comes back. So after it's back in the order that we expect, then we'll write it to the data array in the correct order. And the fragment that's at the head of the FIFO that was waiting on this thing can basically then access the data array and then do the same thing that we did on a hit, right? Because now it's back. And that data may be filled like before it gets to the head of the FIFO, that's fine. It won't be evicted. If it said it was a hit, it won't be evicted because there won't be enough accesses in between, right? Remember in 565, when you study LRU, right, all you care about is when you study replacement policy, you just care about the access stream. You don't care about the timing. You just care about what happened when, like A, B, C, D, E, like all that stuff you looked at. I think they cover Belady, right? When we talk about Belady optimal. It doesn't really depend on the timing. It only depends on the access stream. And that's the same thing that's happening here. Okay. And the same thing, you filter it, which is basically some, linear interpolation operation that's trying to figure out what the color should be in between the 2 points in between the two values on the texture maps. Okay, so you can change, so that's how it works for graphics. And in the early days of GPUs, and even still today in some lower end or graphic centric cards, they didn't want to bolt a shared memory together with the L1D. In fact, there was no shared memory. Well, was there in the very earliest CUDAs? I don't remember if there was, but it wasn't very big. But they didn't want to didn't want to mess with that scratch pad. That was going to be like, okay, scratch pad is on itself. And then if you're going to global memory, you know, good luck to you. And, you know, we'll maybe throw you in the texture cache because if there's some spatial locality, you should be better. So when you did a global memory load, and even if you do a global memory load today on a Pascal GPU, which is now several generations older, the access doesn't go to that shared L1D scratch pad structure, it goes to the texture cache. And the result is that your cache hit time is like 70 cycles. That's not true with the shared memory structure, right? We studied that the cache hit time is only a few cycles, just like the shared memory operations. But if you bolted if you're caching stuff and you bolted the global memory or the sort of general CUDA accesses onto the texture cache, then they're going to be super high latency. In a lot of workloads, this doesn't matter because it still effectively filters the bandwidth, or you just have no locality whatsoever and you're just streaming anyway and none of this matters and you can just bypass the L1 cache. So that's why they did it. And AMD does this too. I don't even know if I think that even today their architecture still put the general accesses through their texture caches. So their hit latency is super long. But again, if you've got spatial locality, it's good for throughput because you will still filter stuff. So it's better than nothing. Questions? And so you can, you don't have to have special instructions to access this. Like if you just do a global load on a Pascal machine, it will translate that and send it down the texture pipeline. It'll bypass all that filtering crap, right? Because you don't need that when you're doing a general purpose access. But it'll just use the SRAM for the texture cache to access this. And even today on like a Hopper or the new, what's the new one called? I just showed it, Blackwell. They call it Blackwell. You can still access the texture unit in CUDA, and it'll just send your accesses down here because if you're really, really meticulous, you want that 16 or 48K worth of SRAM, right? Because it's not something you can use unless you use texture accesses, and we'll send them down that pipeline. But then you have to write the CUDA such that your memory access is a texture access, which is challenging. Yeah.
Well, I have two questions kind of related to that. The first one was, when you do that, will it always do general access to the texture? Will it always bypass the filter?
Yeah. If you're routing those general purpose loads to the texture cache, it bypasses the filter.
Okay, and then the other one was the cycle time.
Yeah.
In general, for a texture cache access, is it higher than shared memory?
Yes.
Significantly?
So you're talking like 50 to 75 cycles versus 2 to 5 cycles. So it's significantly higher. Again, usually doesn't matter. Counterintuitive to all the CPU stuff you've thought about, usually doesn't matter because you can hide those cycles with other warps, typically. Other questions? Yep.
Do you ever store with the texture cache?
No, it's a great question. No. So textures generally are read-only. I didn't mention that. So there's no writes. I didn't show you how a write works because it doesn't happen. Okay, so it's only read-only memory you can put in the texture cache. Okay, so you know, in these early architectures, if you wanted to cache things, you couldn't cache read-write data at all in the L1. Because you can cache it in the L2, but you couldn't cache it in the L1. Good question. Other questions? Yeah, because graphics doesn't work that way. Like they don't write to the textures at runtime. You can do fancy things where you're sort of messing with the textures, right? But then you mess with them in a different memory space. You don't write over the source textures that's in memory. The texture cache is built for read-only memory. Again, makes it more efficient, right? I don't have to build to deal with writes. I don't think about write traffic at all. Okay, great question. Other questions? Yeah.
If you can like access the texture cache,
Yeah.
inside CUDA, does that mean the spawn the kernel that uses the texture cache within the kernel?
Yep. you can look at the CUDA API. It's like read text 2D, read text 1D. It's got like 5 arguments you got to give it.
So then is that access going, since that access from the GPU is like going all the way down to the CPU and back up the GPU?
No, it's going to the, so if you write a CUDA program where you've used this intrinsic that says load from texture, like that's running on the GPU, like that's going on the CPU at all. You have to copy the texture into the GPU, and you have to make sure that your data is encoded as a texture, right? So this Z pattern, right? Like that the textures are encoded with. You have to make sure that that if you want to put a matrix or a vector inside something that's going to be cached in the texture unit and treat it like a texture, you've got to make sure it's processed like a texture and then copied over into the GPU memory. But once that's done and the kernel is running, then you can just go ahead and access it with the texture cache. Does that make sense? So there's no back and forth. After you sort of spawn the thing, you're done.
I was going to ask him about the host itself is the GPU as well.
If the host itself is the GPU, what do you mean?
Like if you're spawning a kernel inside.
If you spawn a kernel inside a kernel, every time you spawn a kernel inside of a kernel, well, what happens today is you will go back to the host, right? Because it's like it has to go into the kernel spawn engine. Now, I don't know if they've optimized that, but in most recent generations that we've looked at, if you do this dynamic parallelism where you do your triple brackets inside of a kernel, which you have to be very careful with, right? Because if you're running 20,000 threads and they all try to spawn 20,000 kernels, and then they all spawn 20, like this is ridiculous, right? You really have to think about what you're doing. You have to go back, you have to insert those kernels into the stream queues, right? And then they're going to get, then in turn scheduled. So that's kind of independent of the texture cache. I don't know if that answers your question, but like, yeah, if you want to use this dynamic parallelism thing to spawn kernels inside of kernels, the only path that I'm aware of is that it goes back to the CPU to put that in there. Now, could you envision hardware that allows you to short circuit that? Yes, but now there's contention, right? Because now the CPU could also be putting stuff in, right? You're trying to insert to a shared queue. How do you do that without coordinating the shared queue, right? Because you need to support the GPU inserting stuff into this and the CPU inserting stuff into this. You could have 2 queues, now you need a priority system, but generally it goes back to the CPU to do this. Okay, but again, this has nothing to do with texturing. This is just what happens if you try to use dynamic parallelism. That makes sense? Good question. Other questions? All right. Okay, let's talk about the L2. So this is the big picture, again, of what the GPU looks like generally. We've got a bunch of the SMT core is basically your SM, grouped together into these clusters, connected, together to an interconnect that is then connected to a bunch of memory partitions, each of which is a bank of your last level cache, and the GPU, the last level cache is the L2. Okay. And then you've got an off-chip memory channel associated with each of these memory partitions. Okay, so the L2 is this. It lives out here on the memory partitions, and it's spatially subdivided across each partition in a banked way. So you've essentially got a slice of the L2 for each of the memory channels in the GPU. And the way the memory is arranged, we'll get to, because we'll talk a little bit more about DRAM after this slide set. So for now, just sort of assume that, this is one channel. So if you have a miss here, you're going to go off to the DRAM system, and we'll look at the details of that later. And the mapping here is 1-to-1. So there's one partition per channel generally. The interleaving here, so if you're gonna take this and you're gonna interleave the physical address space, right? Because you've got some physical address space that you need to spray across all of these memory partitions. This happens at a particular granularity, right? The granularity that we've kind of observed them doing this at is 256 or 1K bytes per partition. So you'll have a consecutive 256 bytes in each partition, or a consecutive 1024 bytes in each partition. And then how you sort of swizzle that around, that is some of the magic. Okay, because trying to spray that around in an equitable way, because the only way you get at the peak bandwidth, the sticker bandwidth on the GPU you bought, is if you use all of these memory partitions at the same time. So you need to make sure that your accesses are sufficiently scattered across all of them. And depending on the way you've coded up your program and the access pattern, you may screw yourself, right? If you've got some weird striding patterns and the mapping isn't good, then you're gonna basically have partition conflicts, okay, in your memory system. And you can get around this with clever partition mappings, and we'll talk a little bit about that when we get into the memory system. But for the purposes of the L2 is going to be, anchored in each of these partitions, and you're going to have a bank in each. Questions on this big picture? All right. Yeah, this is the memory partition. That's fine. Okay, so how does this look? How do we even know how this looks? So again, this is lifted from a patent on, what a memory partition looks like. This is NVIDIA. I think this might be an AMD. I think this is an NVIDIA patent. So the L2 cache is here. Now there's this thing called the FB, which stands for frame buffer, and then this thing called the ROP, which stands for raster operation unit. We'll talk about that in a second. The idea is that this is the interconnect. So this is the stuff coming from the SMs and then going back to the SMs. This is that crossbar network that it's going to communicate with. Before it goes out and tries to go to the memory system, it checks to see if it's in the L2 cache. Okay, so if it's in my L2 cache, I don't need to go out to the memory system, and I can just directly service the response. If it isn't, then I have to basically go out to the memory system. It goes to this thing that they call the frame buffer, which is basically just a memory access scheduler. Okay, something that's taking in, so you're taking in all of the memory requests that come out of the L2 cache, so all the L2 misses go into this buffer, which can then, it's basically a memory controller, right? That'll attempt to schedule all of the misses in the L2 cache to the main memory system. There are intelligent ways you can do this. Simplest thing to do is a FIFO, right? You just take them in order and then spray them out of the memory system. The downside of a FIFO is that things like row buffer locality that we briefly touched on doesn't get captured naturally, right? So you might actually want to do some out of order scheduling here in the frame buffer. So if you look at the composition of a advanced memory controller, it looks a lot like an out of order core on a CPU because you're reordering the memory accesses to try to maximize memory throughput in some way. And that's essentially what's inside the frame buffer. How do they do this exactly? Secret sauce. Okay, we don't really know what's going on inside the frame buffer to try to optimize things. Is it fully out of order? It's expensive to do fully out of order out here at these memory controllers. Is it partially out of order? Is it just a FIFO? It's actually very hard to even reverse engineer what this is doing. Then there's this other thing called the raster operation unit. So rasterization is this process of trying to finally figure out what the final 2D value is on a screen when you're doing this raster-based rendering, right? You've got all these 3D objects and you rasterize it and then you project the final pixel on the screen. It turns out that a lot of operations in this process, you don't need to suck the data all the way back down into the core to do. So for example, something called alpha blending. Does anyone know what alpha blending is? Any graphics wonks in here? What does alpha blending mean? What does alpha mean in the context of graphics? Does anybody know? Yeah.
That'd be transparency.
Transparency. So what do you think alpha blending means?
Like trying to reduce the net, or blend to the alpha value then, so you have more like tiles of alpha values.
Sort of. So transparency is key, right? So every sort of point or every triangle on your screen has 3 color values, RGB. Then it also has something called an alpha value. Okay, if you've got, I think alpha 0 is fully opaque. Okay, that's like this pen. You can't see through it. So if you're trying to project this pen onto the screen, then you can't see what's directly behind. You can't see the part of my hand that's behind the pen. So the only color I need is this one. If my pen was slightly transparent, is there anything transparent in this room? I guess my water, right? So my water's here, right? And so you can sort of see through it, and like some of the colors of my face show up like in some distorted way, right? When you look through it. And so when you're trying to render that, that means that you would sort of like, if you're looking at what color this pixel on the screen should have, it should have some of the color of the bottle that's going to have an alpha value that's going to be non-zero because it's going to be sort of see-through. So maybe that alpha value is like 70%. It's mostly see-through. Then the water's alpha value is I don't know, like 90%. Water does these weird things too, where it refracts the light, right? You have to fake that. Trying to do water, trying to do hair, trying to do trees and raster-based rendering is all just black magic, right? It's like a bunch of hacks to try to make it look like how water actually looks. Because like the light bends, right, when it gets in here and then bends on the other side. And then when you see it, you see this really messed up image. So water is weird. Water's a bad example. Picture this as empty, I guess, okay? When you get to the other side, you're seeing some parts of my hand. So I need some of the color of the bottle, some of the color of the water, if it's in there, and then some of the color of my hand, which eventually is opaque, right? So then you can't see anything behind my hand. So these three things need to go into the color that's on the screen, and that's what alpha blending does. Depending on the value of the alpha, which is how transparent the thing is, that says how much of that color is going to go onto that pixel. Okay, so the final render that you see of this pixel, is a lot the water bottle, because the alpha's, its color is pretty, looking at it this way, you get a lot of the water bottle color, but then you get a little bit of the color of my hand on the background, and then some of the color of the whiteboard on the places where my hand is not there, right? So this alpha blending process means that every time you render a scene, you have to figure out how close every object is to the camera. And then you need to, if they have an alpha, you need to then blend those things together. And this is super common, right? There are a lot of things that are opaque, but a lot of things are transparent or even slightly transparent. And to make something look realistic, you have to have this transparency in your scenes. So this blending operation basically means that I need to draw my hand, and I need to draw the water, and I need to draw the bottle. And then I need to take all three of those colors and I need to blend them together to create the final color. And I may be rendering each of those things like in different places, right, on different cores in the machine. And then that final process of like putting them together, I want to avoid having another bunch of loads to aggregate the data all the way down in a processor, blend those things together and send it back, right? Because that's what you would do in a general purpose system, right? I would figure out all the three colors, I would store them to memory, and then I would load them back in and blend them together if they weren't all being done in the same place. But that's inefficient. So why don't we use some type of processing in memory to do this? This operation is so frequent in graphics rendering that I want to do the blending, not in the SMs, the cores that are good at doing this texture rendering. I want to do this blending up here in the L2 cache. And so this is like a little processor in cache kind of thing that does just this blending operation. And you can sort of, because the graphics rendering is so predictable in what it does, you can make sure that, the stuff that ends up in the same place ends up in the same partition, and then you can sort of blend together all of the alphas together. So this will basically be doing some very simple math up here in the L2 cache to do this rasterization step. Questions on that? So when it comes to CUDA and general programs, you don't care about alpha blending, right? Like that is a very particular operation. But there are some things that you would like to do potentially at the L2 cache, which is not, it is sort of coherent in that there's only ever one value of each, every address that's in the L2 cache is only going to be in one place in the L2 cache, okay? Because it is a memory side cache, which means that if I have atomic operations, I can do them here in the L2 cache. So they use this, or at least they used to. I don't know if they still do. They probably still do in some ways. If you have a global atomic, right? So that you can't, there are instructions inside CUDA that will allow you to do read, modify, write, like atomic read, modify, write instructions. They will send those out as special operations to the memory partition, and then they will do the read, modify, write in the L2 cache to avoid having to load the, because if you've got to load it and store it somewhere, then somebody else can get in the way, right? This is the coherence problem that is a huge issue in CPUs, right? When you try to do read, modify, write in an L1, it's kind of a pain in the butt, right? That's what you did in 437 for those of you who took 437, right? I think you did load, link, store conditional, right? You had to implement that. That's it. Imagine trying to do that in a GPU with like all these threads trying to modify something at the same time. It would be disastrous. So instead of trying to suck the data into the L1 to do the read, modify, write, we're just going to do the read, modify, write out here in the L2, where we know there's only ever one copy. So I know that it's not going to get messed with while I'm trying to read and then change it and then write it back. Okay. And this is part of the reason why atomics are just so damn expensive in the global level in GPUs, because you can't do them in core. You have to send them out here to the memory partition to do them. So they're gonna be lower throughput, higher latency. It's a much more difficult process than if you're trying to distribute it like with CPUs. Okay, questions on this? Yep.
So the cache blocks where you're doing the atomic operations, those don't ever go to the L1.
Yeah, good question. So if you are trying to atomically modify a data value, you have to make sure that is not cached in the L1. Another performance hit. Because otherwise, no one will see the update, right? So you have to explicitly say this thing should not be cached in the L1. This is a global shared value. It'll bypass the L1 and it'll only ever be stored in the L2 at best. Okay, good question. Yeah.
Won't this ROP be like super contended for? You have to like do these like calculations for every single point.
Yeah. So if you have, that's why you're not really supposed, I told you guys you can do global memory communication in CUDA, but like, yeah. If every thread is trying to atomically operate on, you know, huge amounts or even subsets of the data, you know, think about the throughput you have in a GPU compute wise. Your SMs are just horsepower, right? They're just floating point machines. This is not, right? This is like some dinky little thing that's out there just trying to mess with L2 cache lines. I mean, you could beef it up, but then like, we want to put a whole SM out of the memory partition now? I mean, is that a good use of resources? It's a design decision, right? So yes. So generally, if you want to do global type synchronization or global type communications with these atomic operations, it has to be very, very targeted for it to make any sense at all. A lot of programs just completely elide this by breaking anything that needs a global communication into 2 or 3 kernels, right? So I do one kernel, then if I need to distribute the data, it goes back to the CPU, respawns the kernel, because you know everything is done after the first kernel finishes, and then you do a whole bunch of stuff. And as long as you've got enough what we call bulk synchronous data, right, where each operation is wide enough that it can make good use of the GPU, then there's no problem. But any kind of fine-grained communication stuff, it just becomes very, very hard to do it well. Good question. Other questions? Okay. Okay, so we model this inside the simulation infrastructure that you guys use. We model it like this, and we basically have a whole bunch of queues here, and every computing system does look like this. Like there's queues everywhere in a modern computing system because not all the rates match up, so you've got to have FIFOs everywhere in a system. The general way that this works is that so if something is coming in, okay, so something will come in from the interconnect. So let's say it's a load or a store. If it's an atomic, then you'll have to potentially go into this ROP queue to do the raster operation. If it's not, then you don't have to do it. You can bypass it potentially. We actually have profile things, and it seems like all of the accesses go to the ROP queue because the latency here is way higher than what you might expect. L2 latency in GPUs is super high, and it's probably because they don't mess with it to try to make it better for latency. So it's historically means you have a lot of delays. So then you have a little queue here that is basically buffering everything that comes out of the interconnect. And then eventually, once you've got enough bandwidth at your L2, it'll check the L2 bank to see if it's there. If it is in the L2 bank, then it'll route it back and you have cache hit in the L2 and it'll send the data back down to the L1s. If it was not, then it will go into another queue where it will wait for, some time on the DRAM. And again, like the L2 is way faster than the DRAM, right? So you need queues to buffer things. So then it will wait here. And then there's, in simulation, we have another latency queue because we try to figure out like, well, what is the actual latency to do these things? This is a bit of a software, design decision to try to model how long these things actually take. So if you look at the code, it does look like this. And this is why, to just try to model latencies. Then eventually it'll go to the DRAM access scheduler, which will have different algorithms to decide, based on what's currently in flight, what I should schedule next. Then you'll send it out to the DRAM. DRAM will service it. The simulator you use has a model for DRAM, so it will model, row buffer hits and this kind of thing. It is a variable latency DRAM. system. Then eventually it comes back, it goes into yet another queue to wait for the insertion into the L2, because I need to fill the L2 when it comes back. And then once it fills the L2, it'll go into the other queue to wait for the interconnect. Because again, remember, all of these things can be contended, right? There's other stuff in the interconnect. There's other, cores trying to access this particular bank. So there's queues everywhere to sort of handle all of those delays. Okay. If you were doing an atomic operation, then that atomic operation would happen here after you either had the hit or the miss finally returned and you could do the operation. So yeah, this is mostly just an overview of how this is modeled in the simulation infrastructure. Questions on this? Bunch of queues, an L2 cache bank, and then an off-chip partition. That's it. All right. What's going on at the L2 cache? Generally, these things are sectored, and they're sectored with 32 byte sectors, subblocks, and that's because that matches the atom size of GDDR. I think 7 is the latest now. Same with HBM. They usually do this in write back because why would I write through? I don't want to waste my write traffic to the DRAM. I want to try and keep it in the L2 as much as possible. There's no coherence implications because it's a memory side cache. So they're configured to be write back. Optimizing the memory bandwidth, they do the same thing that the L1s do, where if you have a coalesced write, it's not going to read the whole line from DRAM. It's just going to write it right away. Because that's very common that you have a fully, write that's going to write to all 32 bytes of a sector. We don't want to load that sector in and then overwrite the whole thing. So that optimization is in there. Uncoalesced writes are a lot more challenging. Again, uncoalesced write means that I'm only writing to a fraction of the sector. The default thing to do in a CPU is to fetch the sector, so the sector is valid, and then write to it. But there's some evidence that they don't do that, that they may just, have partially valid sectors that you really can't hit on. Because the pattern of writing to something and then reading from it in the same GPU kernel is very rare. Yeah, that rarely happens. So the only reason that I would try to fetch the sector and properly fill it is if I knew that I may have a read, that was going to touch another part of that sector. If that never happens, then it's kind of useless for me to bring in the whole 32 bytes. So they may have some masks in there that if the thing has been written to, then you can sort of cache it at the L2, but then you can never actually hit on it until the end of the kernel when it all gets sort of flushed out. Okay, not a big deal, but writes are a little bit more challenging. Questions? That's it on the caching system. Okay, so this brings us to the end of the core and the design of the memory hierarchy in GPUs in general. And we're going to segue into what the DRAM looks like. So before we move on, are there questions on any of that last piece? You're very quiet today. All right, let's move on. Okay, let's talk about DRAM. So the first part of this, because I don't know how much you really learn about DRAM in other classes. Other than the row buffer thing, so you learn about row buffer in 437, right? Yes? Yeah. Do you know what I mean when I say rank? Rank of a DRAM? Not necessarily. Channel, have you heard of channel before this class?
Yeah.
Where?
565.
565 does memory channels?
Yeah.
Okay. So some of this might be, some of it will be a little bit of review, and some of it will be more stuff you haven't seen. Okay. So we need to fix, so what I want to do is talk about GPU DRAM, talk about HBM in particular, and graphics DDR. But before I do that, I need to make sure that we sort of have a solid understanding of what's going on in a general DRAM subsystem. So some of this I'll move through fairly quickly because maybe you've seen a bunch of it before. I know I've showed you a bunch of it before. I've taken these slides from a guy named Onur Mutlu, who's a professor in Switzerland now. He did CMU for a long time. Done a bunch of work on DRAM. Anybody heard of Rowhammer? Yeah. The Onur Mutlu is the Rowhammer guy. Okay. He's done a whole bunch of other things. Like if you're into architecture and you sort of are keeping track with what's published in architecture conferences, Onur Mutlu is like the most pervasive publisher in the last 20 years. Okay. He just publishes like crazy. So anyway, and he's a pretty good teacher and he made these slides. All right. So you can sort of abstract a memory system. A memory system actually has levels, right? Sort of, we talk about these pyramids when we talk about cache hierarchies. We're like, okay, there's the L1 cache and the L2 cache and the LLC. And then finally you have DRAM and then maybe a backing store or something. So we look at that pyramid of what a memory system looks like. DRAMs also have a pyramid-like structure. Okay, so you sort of touched on what a memory channel is. So memory channel generally means we have a memory controller on chip these days that is controlling some pins that are connected to a memory of some sort. Okay. So a channel is sort of a one-to-one mapping to a controller and pins coming off of the main chip that go to memory. Then we have these things called DIMMs. Okay, what does DIMM stand for? Anybody know? Yeah.
I think it's like dual inline memory model.
Yeah, dual inline memory model. Like that's what you buy, right? If you build your own PCs, these are the things that you go to Best Buy or whatever and shove into your motherboard. These are DIMMs. Okay, these are DRAMs. They're modules that plug into some interconnect that will, the motherboard is then routing all the signals from the DIMM into the chip. Okay, and then the memory controller, the channel, is the thing that's sort of perturbing all those lines and getting you the data. The memory controller has to know how that chip operates. That's why we have standards, right? That's what JEDEC is for. That's why there's DDR3, DDR4, because it's like, I want Micron to go build DIMMs that adhere to one timing standard, and I want Intel or NVIDIA to be able to build chips that have a memory controller that know how to use that memory standard, okay? So that interface is JEDEC's job of like keeping that because there's very specific timings, right? Like the JEDEC will say it takes this many nanoseconds to do this particular task, and then your memory controller has got to make sure that it's sending those requests at that particular rate. And if it's too fast, then the memory doesn't have a responsibility to keep up. It's like, oh no, I'm GDDR3, not 4, so I don't have to deal with this, right? So they have to be in sync, okay? Which is why that standard committee exists. JEDEC is basically the people who make the edict of what is DDR4, what is DDR5, sort of standards committee. I don't know. It's important work, but man, that would be a terrible job. I don't know, trying to build consensus and like find, something everyone can agree on and just deciding on what the particular rates are. Maybe suitable for some people. I would find it challenging. Okay, so we've got channels, we've got DIMMs. Then we have things called ranks. Probably something that most of you haven't really thought about before. We'll talk about what that means specifically. We can sort of think of it like a SIMD for DRAM. Okay, we can bolt a bunch of these things together and control them with the same lines. That will be what a rank is. Okay, then we have the chips. This is very visceral, right? This you understand. This is the little black box, right? I didn't bring in a DIMM, but when you buy a DIMM, well, there's pictures of it. It's this green thing, which is a PCB, and there's these little black things on it. The black things are the chips. Okay, they're individual chips, just like your processor is a chip. Inside of each chip, there's a whole bunch of banks. Okay, there's a lot of parallelism just inside each chip. Why? Well, because accessing one bank takes a long time, so I got to shove a bunch of them in there so I can overlap the accesses so that the pins on the thing are kept busy. Okay, and then inside each bank is the sort of square or rectangular structure you're used to. We've got a row, you've got a column, okay? All right. So at its very bottom level, there's these 2D cells, rows by columns, which we've talked about. DRAM row is also called DRAM page. We love to rename things in computers. So like a page, operating systems use pages for the virtual memory system. DRAM manufacturers, if you go talk about pages, they're talking about rows, which is basically just how wide your chip is. Like when you light up one DRAM row, they call that a DRAM page. There's these things called sense amps. Okay, anyone who does VLSI knows these very well. These basically detect very small changes in voltage or current across two lines to try to very quickly read out whatever is in the cell. An analog circuitry, probably the most complex analog circuitry in modern systems that it gets used all the time. Sometimes this then gets latched into some sort of storage cell. Sometimes it doesn't. You're just reading the raw output of the sense amps. It doesn't really matter. What matters is that this is called the row buffer. Okay, so you bring the stuff down to the sense amps, and whatever bits they're blasting out, that is what the row buffer is, because that's sort of all of the wide things that you read on this particular cycle. When you access a DRAM, it's not like an SRAM where you sort of just give it an address. You have to do it in multiple cycles. Okay, so you have to first send a row address and there's a long time to turn on the row, and then you send column address. So there's these things called RAS and CAS. You probably have seen these before if you've talked about DRAMs. Row address strobe, column address strobe. These are timing numbers on how long it takes, once you send this command for it to actually do that particular operation. So when the memory controller is spitting stuff out to the memory chips, it's going to have to first send a row command, light up the row, and then it's going to have to send several column commands to read each of the columns. When a row is closed, meaning that it is not currently on the stamps, we have to do several things. So we first have to activate that particular row. So there's an activate command, and there's timing associated with this for whatever flavor of DDR you want. And after that sort of activation command, it's that the value is placed on the row. Then you need to read and write each of the individual columns, because you need to read out some piece. Like the chip itself does not have enough wires coming out of it to read out the whole row, right? That would be a crazy design. It would just be too large. So the chip itself is going to be wire limited. Everything here is wire limited, because you've got wires running across the PCB, wires running across that PCB that's inside your DIMM. So you're going to have all this storage shrunk down into these like small amounts of pins that are coming out of each IC or each bank. So I'm going to read out, some quantum of each of those rows with specific commands. And then I need to do something called pre-charge. So that basically will close the row, right? Because if it's a DRAM, these reads can be destructive. And you need to make sure that after you close the row, you charged it back up. So there's a pre-charge command here to close the row and then prepare the next bank prepares the bank for the next access. Because again, I'm going to have to charge up all of those lines. And then when I know what row I want, I'm going to open that row. So I have to do this pre-charge process to essentially put everything back in a known charge state before I go open my new row. So and these processes are slow. This is why it sucks to move rows, because I have to do this pre-charge to make sure I can go read the value from the next row. And then if you've already got an open row, so that means that you've already, lit up an entire row of one of these things, then you don't need to activate because the row's already on, and you can just continue to issue column read commands. So here is this is the cartoon that's pretty, it's very illustrative, but you guys probably know this already, right? So it's a rectangular structure. I have to have a row decoder and a column decoder. The row buffer is essentially what the sense amps are pumping out. If I want to access, let's say, row 0, column 0, so the very this is upper left, right, of your perspective, then the first thing I have to do is actually turn on that row. So you'll send a row address for 0, it'll turn on row 0, then that'll get blasted out on the sense amps. And then I need a mux down here that's going to take some fraction of that row. I just have some control lines on the mux that essentially takes the column address to try to figure out which part I'm going to put down on the wires that I actually have. The data wires are not wide enough, like they're not a whole row. They're much smaller. You're talking about rows in the order of like 1,000 bits, and then data wires in the order of 8 bits or something for each individual bank. Okay. And again, these can vary, but that's sort of the ratios. Then the data will come out. And then let's say I want to read column 1 from the same row. This is what we call a row buffer hit. That means it's already there. I don't have to do any closing of the row or reopening another one. I can just go ahead and access column 1, and I'll mux that data out. And this is what we want to do generally, right? We want to open a row and then eat as much of that row as we can. Sometimes applications don't play well with this, right? But nice linear access patterns play very well with this type of access. Same thing if I go to the end of the row, it doesn't really matter what place in the row it is, I can still read it. And then if I need a different row, then terminology-wise, this is called a row buffer conflict or a row buffer miss, meaning that the open row is not the one I want. I've got to basically get rid of that and then reopen, right? I have to send the new address and then I have to reopen a different row 1, it gets read out, and then I can read out the data and so on. Okay, makes sense? All right. The chip itself consists of multiple banks, always. The number of banks varies depending on what type of DRAM you have. Banks will all share the same command, address, and data buses. So you'll have your chip, it'll have some wires coming in. Some of the pins will be for commands, some of the pins will be for the data. And all of the banks will essentially time slice those pins, okay? Then the chip interface itself, like I said, is in the order of 8 bits, 4 to 16 bits typically. That's the data that's going to come out. So this is a detailed picture of an actual DRAM chip. I can't remember what one this is, but there's all of these have names, right? They all have like model numbers and serial numbers, and like depending on the widths and everything, and the manufacturer, these will be different. But generally, this is how it works. And I don't want to go into this in excruciating detail, but the key thing to look at here is that these are the banks. Okay, these are the individual banks that I talked about previously. In this particular chip, it has 8 banks. Okay, and you'll see that the inputs to this chip, like the address that's coming in, some 17-bit address, this is shared, right? So you can only ever, on one cycle of this DRAM, you can only ever use one of these banks at a time. And the banks exist because I want to overlap the accesses because they each take a lot of time, okay? Sense amps are down here. Then you have a bunch of circuitry. This is the decoder, which is the column mux. And then there's potentially latching in here. And then eventually it goes to this I/O. All of this is all the good analog stuff that happens to actually drive the lines that drive the data on the output, okay? The actual data pins here are up here. This is the data, so DQ 0 through 7. So this particular chip has 8 bits that gets spit out of this thing every time. And I think that the width, I think the first number here on the memory array is the page width. So 60, is that right? No, the page width is 8K. Okay, the page width here is 8K bits. Oops. So every time you open it up, you're getting 8K bits out of the sense amps. Okay, so 256 by 32. And then 16K is the number of rows. And if you do all this math, you figure out how big the memory chip is, right? This is a 128 meg memory chip, and it's got 8 bits coming out of it. So this is a 128, that's the capacity of this thing. And then 8 bits is the sort of output bandwidth that you get out of it, depending on what clock rate you sort of clock it at. And again, the clock rate will be determined by what type of DRAM it is, okay? Questions on this? I'm not going to test you on the specifics of all this stuff. You probably have seen a picture of this before, at least in some, maybe an SRAM chip, sort of similar, except DRAM has more commands. The data, needs to be refreshed, et cetera. But the general setup is sort of similar. And this is a real, block diagram of a real DRAM chip. Okay. So what is a rank? So a rank is simply just a grouping of multiple chips together that sort of form a wide interface. So each chip, the size of each chip is really determined by manufacturing details, right? Like I would want more than 8 bits on any cycle of this thing, right? But I can't do that in a cost-effective way. So if I want an interface that's bigger, like let's say I want to read out, 32 bits every time, I can put 4 chips together and then call that a rank, okay? And I'm going to control them with all the same control signals. I'm going to have different data, right? Different pieces of the data in each one. But logically, they're all going to go to the same address within a particular chip. And so that is a rank, where I sort of fuse together. It's sort of like, how you have scalar instructions, like a scalar add is going to operate on, 131 float value. You have a SIMD that's going to operate on 4. A rank is like a SIMD, but for memory, where I'm sort of fusing together the control of multiple memory chips together to get a wider interface. So logically, it looks like if I had 4 chips in this rank, it would logically look like a 32-bit interface that had, 512 megs of capacity. There would be no logical difference between that and a giant chip, right? That just had a lot more capacity. You can't build a giant chip, so we have to sort of fuse the chips together to get a rank. Make sense? Okay. That's what a rank is. And so they'll all respond to a single command. They share all of the same buses. Obviously, different data. It would make no sense to have the same data coming out. So when you do the address mapping, you'll make sure that all the writes sort of stride it across that particular. When you're sending the data into these things, you're going to have to make sure that they're getting logically different data. Okay. But that scales naturally, right? Because you're going to have more pins. You're just going to have more pins, and then you're just going to shove the data in and read the data out in wider increments. And so, yeah, it's sort of like DRAM SIMD. That's the way I like to think of a rank. And a DRAM module, so one of these DIMMs, consists of one or more ranks. Typically what happens is the front side of a DIMM is one rank and the back side of the DIMM is another rank. So they're logically like big, wide, you can think of them as two big, wide chips with a lot of capacity on each DIMM. And this is the thing you shove into your motherboard. So if you have chips with an 8-bit interface to read out 8 bytes in a single access, then we have to use 8 chips in a DIMM. Yeah, if they have 2 different ranks. Okay. Okay, multiple DIMMs. So this is what a motherboard could look like. This kind of mess of a thing here. Now, if I have a single, this is CPU. Okay, don't worry about GPUs. CPUs you can plug stuff in, right? You buy a CPU today. There's like a motherboard with a given number of slots. If you plug more DIMMs in, you're usually not getting more bandwidth, right? You're just getting more capacity. And that's effectively because you only have one memory controller that's controlling all of those DIMMs. So that single memory controller is sending all of the same address. And so this is the address and the data wires, and it's sort of going to all the DIMMs, okay? Because I'm broadcasting the same address, and then I'm going to get back, and the wires that I'm using for the address and the data are the same. And then, well, how do I just have a chip select line to decide which one I'm going to use on any given cycle. So when you plug in more DIMMs, you usually don't get more bandwidth unless you're lighting up another channel on your system. So if you have a big system, we have systems in our lab where the CPUs do have more than one memory controller. Some of the DIMMs are tied to one memory controller, and some of the DIMMs are tied to another memory controller. So if you plug in, you're only using one DIMM on this side, and then you plug in a DIMM on the other side, you're lighting up another memory controller, and you're actually getting more bandwidth. But typically you're not, you're just getting more capacity. The downside of this is that the more DIMMs you hang off of these pins, the slower that it gets, right? Because you're hanging more stuff off of the same wires. So when you're manufacturing the motherboard, you don't want to have 100 DIMMs to plug in, because it gets slower as you have to have more, metal hanging off of that. And if you actually plug them in, all of the capacitance from the circuitry hangs off of it, and you get all of these bad analog things that happen when you try to scale out stuff to a crazy extent. But, typical machines do have multiple DIMMs because DIMM capacity is limited and usually more cost effective to make smaller DIMMs. If you bought memory, this is obvious, right? If you buy a 1 terabyte DIMM, if that's even available, it's probably available today. It's way more expensive than buying 2 512 meg. No, I don't think they're that big. What's the biggest DIMMs? Last time I bought them, I think it was like 128 or 256. 64?
64 are the fastest ones, 128 are the.
Okay, and the slowest ones. Yeah. So these machines, these CPUs that have terabytes worth of storage, there's a whole bunch of DIMMs in there, right, to provide that capacity. Questions on this? Yeah.
Better to have like a 16 gig DIMM or 2 8 gig DIMMs?
Better how? Cost-wise, you're better off having 2 8s, typically. Throughput-wise, okay. So I don't know that you really see any difference, because the board is already manufactured to have a slot, right? You're already hanging all those wires off of the thing. When you plug in that extra DIMM, it should not, the whole thing should be manufactured so that at the worst case, we've hung all the DIMMs off of the wires, it still meets GDDR 4 or 5 standards. So if you've only got one, it's probably still just using the slower. Now, memory controllers can get clever, and they can try to be like, oh, this one's actually faster, and maybe I can get away with, there's some OS routines that sometimes are run to try to be more optimal with each memory chip. There's research on this kind of thing. But generally, it's not going to be a difference that you'll notice, except in your wallet. So you're usually better off just buying the 2 cheaper ones. But the real trade-off is the capacity, because if I wanted to have, then I need to buy bigger chips. Other questions? All right. Okay, so that's a single channel system. Even CPUs can have more than one channel, right? If you've got one of these Intel processors that's in a data center that's got like 100 threads or 80 hardware threads on it, that's a lot of memory demand, even from scalar processors. And you'll want to have more pins coming out of the chip and more memory channels to deal with it. It's not like a GPU where we have like 32 memory channels, but you can have 4 memory channels on a CPU system. So a channel is, basically means that there's 2 logically and physically independent memory systems. Whole nother set of wires, whole nother memory controller coming out of the chip that allows you to get, double the bandwidth, double the area, double the bandwidth. Right, like a government project, make double the cost and get it twice as slow. So this sounds good, but obviously it's expensive, right? To put more memory controllers on. And the upside is that these are completely independent, so you can send whatever you want to each thing, but you have to have separate hardware and separate wires and a whole separate system to deal with it. So in this example, I've got 2 DIMMs, but the 2 DIMMs are actually on 2 different memory controllers. So if I only had 1 DIMM, I would have half the memory bandwidth as if I had 2 DIMMs. Okay, because if I only had 1 DIMM, then I'm not using any of this, which is bad. Then you're definitely much better off buying the 2 16s versus the 32, because you'd be lighting up this thing. This case is kind of rare. Usually, if you've gone to the effort of buying a CPU with multiple memory controllers, you're gonna have both of the memory controllers lit up. Otherwise, whoever built your CPU is an idiot. All right. Okay. So we can draw some pretty pictures. These slides like to draw the same thing in multiple ways. Okay, so here's a memory controller. There's a channel. There might be multiple DIMMs hanging off of said channel. If you sort of drill down into the chips inside of each of the channels, then there's, at the very lowest level, it's this, and then we put a bunch of these together to compose one of the chips, and then the chips sort of get composed together to be one of the modules, and depending on the configuration of the modules, all those can go together as a rank. Okay. This drawn another way looks like this, where we'd have this is a system, a processor that has 2 memory controllers, so 2 different channels, and then this has 2 independent ranks. So a DIMM usually looks like this, where you've got we've got 2. The front side is 1 rank and the back side is another rank. And so you basically have to share them temporally over the channel, right? So you're going to light up 1 rank and then light up the other rank. Here we haven't shown the chips. We're just sort of abstracting away the rank as a whole bunch of banks, because you can think about it that way, because it doesn't really matter logically how many chips you have. It just matters how many ranks you have. And then they will all share, this sort of, and we have another one that's sort of independently doing the same thing. Composition of the bus is how you might expect. There's some bits for command, there's some bits for address, and there's some bits for data. Okay, these are the wires that are flowing in and out of this thing. Okay. Here's another picture of loosely the same thing. So a CPU, these are CPU slides, right? It's good to understand what happens in CPUs first. The CPU's got 2 memory controllers, 2 memory channels, connected to 2 DIMMs in this case. This is the picture, right? If you've never seen one of these, which I can't imagine anyone in this program has never seen one, right? Like this is the PCB for the DIMMs, and these are the individual memory chips, these little black things. This is an integrated circuit. Probably people in computer science, but I don't know, who knows? But you guys should know what this is. All right. Yeah, we can flip it on its side. Okay, and then there's the front and the back of the dual inline memory model. And typically this is 2 ranks. Okay, so you got 1 rank on the front, 1 rank on the back, each of which is composed of 8 chips. If each of them has an 8 wide interface, then you've got 64 bits coming out of each of the ranks in the memory module. Okay, so here's another way to draw that. So we've now got, these boxes that basically say the same thing. I'm not going to say it again. You can break down the rank. So just to drive this home, right? Because rank is probably the only thing you didn't know about before this class, is my guess. Okay. So the rank, the look of this is that I've got 64 bits blasting out every time. I get that by clubbing all these chips together, and each of the chips is now giving me 8 bits to sort of get concatenated into the wires that come out of this thing that's giving me 64 bits. Inside each of these chips, I've got a whole bunch of banks, right? Each of the banks has 8 bits. So each of them is only able to spit out 8 bits at a time. And so I'm going to have to select based on what address I have, what bank I want the data from. And then that is the data that's going to get muxed out to sort of come down to the system. And you may be asking, who decides where all this gets placed? This is the job of the memory controller and the physical address mapping, okay? And it's usually fixed because you don't want to screw with this. You don't want to like move it around while the thing is moving. They have to move data around. It's kind of a huge pain. So there's like usually modulo or some kind of index-based mapping, which we'll talk about later, that says, here's my physical. So this is after virtual. Virtual is a software thing. Forget about those guys. I've already got the physical address. I have to take each of those bits of the physical address and then say, okay, these bits tell me what rank I'm in, and these bits tell me what channel I'm in, and these bits tell me what bank I'm in, and these bits tell me what row. Like that's essentially the mapping that has to happen here, because the real memory system has to deal with this complexity, right? It is a big parallel system with a whole bunch of stuff happening at the same time. I'm going to stop here for today. Any questions before I let you go? All right, we'll hopefully finish off DRAM on Tuesday, and I'll segue into the GPU DRAM as well to sort of talk about the differences and what is HBM, really. We'll sort of talk about that, okay? Anything? Good? I'm over time. Thank you all, and we'll see you next week. Have a good weekend.